Okay, let's get started. Um, Everybody, can you see my screen?
Yes.
Okay. You see the reason I am showing you this slide. As you can remember, in last class you were solving these problems, and then many of you have completed, and some of you are continuing. And then after the class, actually, I uploaded the solutions as well. So as you can see here, number 1, 2, 3, and then in next here, number 4 and 5. So I have uploaded the solutions together with this slide. And that I just uploaded, I think, yesterday. So therefore, those who could not complete on that day or still you are not understanding, please look the solutions here. Okay, so is this fine? Okay, now let's come back. Now, can you see the new slide, new screen about midterm exam 3?
Yeah, we can see it.
Okay, oh, great. So as you can see, you will take the midterm exam 3 next week, that is November 10th, uh, coming Tuesday. And the syllabus is pretty short. You have to look class lecture starting from 19 through 22. So 22 today is 21. So 22 means on coming Thursday's class, day after tomorrow. So therefore basically 19, 20, 20, only 4 classes. And then you look all numerical problems, short questions that we discussed, and the class quiz. And then in terms of book chapters, if you see chapter 9 and chapter 10, today I will be starting chapter 10, the transients of electric machine. And then as usual, the question patterns will be the same as the midterm exam 1 or midterm exam 2. And then again, you might expect 7 to 8 questions. So, and then, sorry?
Did you say it was on a Thursday?
No, I said Thursday mean the class lecture 22, that will be on day after tomorrow, Thursday.
Okay, gotcha.
Yeah. So just in advance, I mentioned today it will be 21. And then the syllabus covers until Thursday, that I mean. And then November 10th, I think that is coming Tuesday, next week Tuesday. Okay. And then you remember, as I already told, this is midterm exam 3 and you already have taken 2 exams. So what I will be doing among 3 midterm exams, your list on will be cancelled. So your worst on will be cancelled. For example, you got 95, you got 90, you got 80, just an example. So 80 will be cancelled. So therefore, for everybody, among these 3 midterm, I will be picking up the best 2 towards your final grade. But then if you please take seriously, this is very short and then you are covering the whole thing, whole syllabus. So that's a very good practice for you. Then you all are ready for the final exam as well, the comprehensive final exam. Okay, so anyway, so then today let's start that chapter 10. Chapter 10 is transients and dynamics of electric machines. Like so far we covered lots of machines, electric machines, especially the synchronous generator, synchronous motor, DC motor, transformer. So when we are looking the transients and dynamics of electric machines, basically we will be looking first the synchronous generator and then the DC generator. So now, what is the dynamics and what is the transient? I mean, in real practice, you know that synchronous generator are connected to the power grid. They are connected to the customers. Therefore, first there is synchronous generator, and immediately after that, there will be a step-up transformer, and then long transmission line, then distribution line, again couple of transformer, and lots of equipment all the way, and then finally customers. Now, what we will be discussing, so let me take you to that whiteboard for a moment, just a moment. Okay. So what I am saying that, for example, this is the synchronous generator, SJ. So I am specifically going synchronous generator because synchronous generators are really, that available at the power plant. That is the generator which is available. And then it produces three-phase power. And then, so there is a transformer, three-phase transformer, and then the line is going on all the way. And then I'm just showing very simple and then brief schematics. Here are the customers. Customers are connected. Again, there can be many step-down transformer. And finally, here the loads. Like it could be three-phase or it could be the single phase. Now, and then you all know that, of course, because this is synchronous generator, so there is mechanical input power. So this is the shaft system. That shaft is rotating at a certain speed. Now, so far we concentrated on synchronous generator, how much voltage it can produce, what is the voltage regulation, what is the impact of power factor, what is the excitation, what are the conditions to connect to synchronous generator in parallel. We studied a lot about this. Now today when we will be looking the transients in electric machines, the transient means, for example, everybody see these are the line, transmission line. And for example, suddenly a short circuit happened. The nature of the short circuit, this is like A phase, this is B phase, and this is C phase. You see, all three phases sorted out for some reason. I mean, I am gradually coming that point that how the short circuit might happen. Anyway, so at this moment, everybody see that there has been a short circuit here. And then because that short circuit, now think couple of points. So here is the mechanical power. PM is the mechanical input power. And it is producing electrical power, which is PE. This is electrical power. And there is an equation which is called the swing equation. Everybody see that phi equal to Pm minus Pe. So that phi is the, let me level, that phi is the electrical power. This is electrical power, and that this is the mechanical power. And P is called the accelerating power. So P is called accelerating power. And then during normal conditions of the system, in ideal condition, this difference should be zero. So therefore, everybody see what I am discussing, that this is a synchronous generator. It has the mechanical input power. And that mechanical input power is coming from the fuel sources. Whatever it is, nuclear turbine, gas turbine, oil turbine, steam turbine, wind turbine, whatever it is, there is fuel input. And I am assuming that mechanical power, which is PM, that is constant. And I am assuming that there is no loss in the system. Of course, there is frictional loss, windage loss, resistance loss. But at this point, ideal condition, I am assuming there is no loss. Consequently, I am getting the electrical power, which is equal to the mechanical power. So you see, and then that should be zero. That is the ideal condition. Now everybody say, you remember I started talking that this generator is connected to the loads, customers, via the transformer, transmission lines, again transformer, and there could be other equipment. And suddenly a short circuit happened here. So everybody see, what is the meaning of the short circuit? So what should be the voltage here? If it is short circuit here, what should be the voltage here?
0.
0, right? Yeah. So therefore, let's say it is close to 0 volt. Now you see, what is the phi? Phi, I said this is the electrical power, electrical output power. So what is the phi? So phi is your VI cosine theta, right? I mean, of course, and this is 3-phase, so I should multiply by √3. So √3 VI cos theta. So whatever the power factor was, because you see, here the voltage becomes almost 0 or exactly 0. Consequently, on the primary side, that will also be 0, whatever the number of turns. Ultimately, your P electrical output power, it will be close to 0. Or at least it will be very, very low value. You can say that. So therefore, now everybody see this equation. If your P becomes 0, so what should be the result here? So there will be positive value, right? It will no more 0. There will be some positive value, you can say. Because I am assuming that Pm is constant. Everybody keep in mind, I am assuming that mechanical side, the fuel input, the shaft system, everything is fine. This short circuit is not doing anything on the fuel input. That is my assumption. Now you might argue that, okay, what if there is any, so that is different thing. If there is any problem on the mechanical side, definitely the system will be shut down. It cannot produce any power voltage. That is different thing. But at this point, what I am saying, everybody assume that your mechanical side is fine. Consequently, what I am saying that mechanical power is constant. This is fine. What I am assuming, I am concentrating on the electrical side from this point to until the load. If there is any short here, that will make your phi goes to 0. Then what will happen? There will be fully like Pm value will be available here. Like this result will be, or at least you can say it should be, it must be positive value. So this means that if it is positive, then that is the accelerating power. So what is the accelerating power? What does that mean? That phi A equal to Pm. Meaning is that this shaft will start spinning at a very, very high speed. For example, initially it was running 3600 RPM. Because of this short circuit here, and according to this equation, because now there is accelerating power, this shaft will be accelerated. This means the speed will go beyond 3600 RPM. That will be the impact. So this is one situation. Then everybody see, for example, it is not the short circuit. The system was running fine. The Pm minus P was 0. What you did, so you are the customers. Here are the loads. Somebody suddenly injected more load. For example, you increase another 10 megawatt load in the system. So assume that your PM was 100 megawatt and your P was also 100 megawatt initially. And then the system was balanced, the result was 0. What you did, you suddenly injected 10 megawatt load. Now your P got 110. So if it is 100 and here it is 110, what will be the result? You will be getting negative value. Whatever I am just giving example 10, it could be a very high value. So if this is bigger than this one, so you will be getting negative value. So then what does that mean? So your equation is phi equal to phi minus phi. And then now you got phi equal to negative. What does that mean? It will be decelerating power. I mean, I said that is the accelerating power, but instead of acceleration, it will cause deceleration because it is negative value. So what does that mean? That shaft will start rotating much lower speed than rated. For example, 3600 is the rated normal, maybe 3200 or even it could be much lower. depending on how much load has been added, how much negative it is. So this means that what I am saying, that on the electrical side, if you make any change, either short circuit, or you are injecting some load, or you are taking out some load, depending on situation, the impact will go on the shaft system. Either the shaft speed will increase or the shaft speed will decrease. And what will be the consequence of that? Can you guess? If the shaft increase or shaft decrease, what will be the frequency here? The frequency will be changed, because you know that F is that Pn over 120, where Ns, where Ns is that synchronous speed. So everybody see, if your Ns increased, meaning that your frequency will increase. So this means when here the result is positive, when it is acceleration, shaft will be accelerated, consequently speed increase and then frequency increased. On the other hand, when you are injecting loads, because P getting increased, it is overloaded, it is facing much more burden, consequently system will be decelerated. Because speed decelerated, your frequency will be decreased. But then what is your requirement here? So as a customers, your requirement here to get 60 hertz. Because you are customers, you are connected here. So therefore, whatever happens to the entire network, starting from the fuel input, all the way, whatever happens as a customer, you want to get 60 hertz. Because if it is not 60 hertz at your home, in industry, in building, in school, college, whatever the load is, your system will be interrupted. Your device will be affected. But then we noticed when the P goes 0 or P goes the very high value, and because of that phi become positive or negative, that is causing frequency change of the system. That is problematic. And this situation is called the transient situation. This phenomenon, that this short circuit, for example, as an engineer, you are working. These are the overhead lines. You are working here with the ladder and you are fixing something, but by mistake, you got short circuited among all three phases, or you made short circuit between two phases. It could be all three phases or between two phases. You made short circuit. And then immediately you realized, I made a fault. But by then, because once you made a short circuit, even though it is like in millisecond or microsecond range, immediately there will be impact here. Immediately the impact will go on the shaft. Or suddenly it is not the case. You did not think about the whole situation, what will happen. Suddenly you injected some load, or you take out some load, big amount of load, 10 megawatt, 20 megawatt. It is not the case of the house. Typically, it is the case of industry. Suddenly they did something. Then the impact will go on the shaft. So that's why this situation is called the transient. So meaning that your generator was running fine initially, everything was fine. The fuel side is fine, mechanical power is fine. But then because of some issue on the electrical side, the impact will go on the generator. Now, you remember the beginning of the semester, I was telling the distance from this generator to until the load point, it could be 1,000 mile, for example. You don't know. It could be 1,000 mile. But still, whatever happens in this side, the impact will go back to the generator and until the shaft. That is pretty interesting. And if it is frequently changing, that shaft is continuously like increasing, decreasing because of this situation, then at some point, shaft will be damaged, which is not desired. So this means then what to do? I mean, that we'll be looking and discussing. Oh, what is the solution? What to do? That is the different thing. But everybody try to understand that due to any fault or any load change, the impact is going on the shaft. This situation is called the transient, and that is the subject matter of chapter 10 that we will be looking in details today. Everybody, could you follow me what I am saying?
Yeah, it makes sense.
Yes. Okay. So now go back to that slide.
Yes, sir.
Okay, great. Okay. Now everybody come back. So that I wrote that equation. Now it will be helpful for you. Swing or power balance equation. So therefore the equation that I wrote there, everybody see that phi A equal to phi M minus phi A. And I have defined those on phi is accelerating power, mechanical power, everything it is written. That is called the swing equation. So sometimes in the AP exam, you might be asked this, can you just write down the swing equation? Simply, this is the question. So then you should just write this one, that phi equal to phi M minus phi. Or sometimes it is called the power balance equation. And then actually I was explaining you that phi A, that mechanical accelerating power on the mechanical side, and then that is md square delta over dt square. So you use the symbol delta, which I call the power angle or the torque angle, or sometimes it is called the rotor angle of synchronous generator, and m is the moment of inertia. Moment. So from the physics, you know that moment of inertia. So because it has a mass, it depends on the m value depends on the size of the generator. If it is very big size, like 200 megawatt, 300 megawatt size, accordingly m value will increase. And if it is a small size, then m value will decrease. So that's why it is called the moment of inertia. So because of this reason, because the rotor angle is involved, accordingly it is called the accelerating power. Because you know the d square delta over dt square from the physics, this is the acceleration. When it is d delta by dt, that is just the velocity. So anyway, and then I said that the P can be changed due to any fault or load change. That thing I explained to you. Now, based on this thing, now everybody see two things. Now, that generator could be synchronous generator that I just explained. So what should be the characteristics of synchronous generator during fault on line? This means that your generator is connected to the system, to the line, and the fault happened on the line. How does the synchronous generator will behave? What should be the characteristics of synchronous generator? So then you see what I have written. Generator terminal voltage drops and oscillates. Frequency and speed increase and oscillate. Active power decreases and oscillates. So therefore see the sequence. Once there is any fault on the line, along the line, whatever it is before transformer, after transformer, or nearby customers, the impact will go on the generator. How I know? So because of this equation. Now in this case, what does that fault mean? So first we need to understand this one. What is the fault? So therefore now fault I was explaining you, fault can be various types. So again, let me take you to that whiteboard that will clarify you. Everybody see, I was explaining you the example of the short circuit. So now there can be various types of situation. Let me clean this portion and here, let me write down those things. Okay, keep this thing. Okay, now when I say the word, you know, the fault, so it can be, this is on situation that three-phase got short-circuited or two-phase got short-circuited, or it might happen that you see three-phase got shorted and then this is the ground. Three-phase got short-circuited and made grounding. So this means this example is, for example, in a stormy day or some storm or tornado, something is going on, and suddenly a tree has fallen, and that tree, branch of that tree, is like touching F edge, B edge, C edge, but its root is still on the ground. It is not fully uprooted. Its root is on the ground, but portions of the tree or branches got stuck on the three-phase, and that caused short circuit. Because the tree is a good conductor. Whatever the leaves or branches, they are the good conductor. There are juice or the sap inside those. So they may cause short circuit. And short circuit plus grounding. So accordingly, there are different types of fault. It is called 3LG fault. It is called 3LG fault. 3LG fault means 3 means A phase, B phase, C phase, 3 phase. So L means line and G means the grounding. So it is called 3 line to grounding fault. This example. Now the next example could be 3LS fault. 3LS fault means it is not grounded, just 3-phase shorted. Just 3-phase shorted. For example, as I told that as an engineer, you were working on the lines, you were doing something, but suddenly you made a mistake and you caused short circuit among all the 3 phases. It might happen. But then immediately you realize that no, I am doing wrong thing, but you created the short. That is called the 3LS. This means 3-line short. So in this case, it is not grounded because you are working with the ladder. So you are fine, you just got. Or sometimes it may happen. Have you noticed that sometimes a bird, like typically it is called the bat, this animal. Do you know this animal, the bat? Sometimes this got stuck between 2 phases or among all 3 phases. It was flying, that animal bat. It was flying and somehow got stuck and then got died because of the heavy current flowing. Or it could be other birds, but like I have seen, typically the bat got stuck. Anybody, have you seen that bird got stuck on the lines? Have you noticed?
I've heard of squirrels getting stuck on the line.
Oh, the squirrel, yeah. So that could be the example, squirrel, but I have seen like the bat, because it has like 2 good wings and it flies with its both wings and then it got stuck. Like one wing is here, then other wing is here, and it's like face is here, mouth is here, and then in that way it got stuck. It cannot. Sometimes luckily they can fly away, but sometimes they cannot. But then once a bird is touching, all 3 phases, that is definitely causing all 3 phases, or it could be any 2 phases, that is causing short circuit. Now, the 3LG, 3LS, and if the short circuit is between 2 phases, for example, between phase AB or between phase CA or between phase C and A, whatever, between 2 phases, that is called 2LS fault. 2LS fault means the fault is short circuit between 2 lines, any of the 2 lines. Now again, it can be, for example, again the same example, on a stormy day, a tree has fallen and its branches got stuck at phase B and phase C, but then its root is here. It is not fully, wiped out or not uprooted, but then branches got stuck between 2 phases. And then this is the grounding, the same thing. So in that case, it is called 2LG. Let me write down this one first here. It is called 2LG. And then the other one I wrote, which is 2LS. Okay, now it may happen that again the same example, because of the storm, a tree has fallen and it is just touching one phases. For example, only one phase, this phase, and then it is grounded. So this means that in this case, the fault is with only one phase. It could be here, for example, this phase, and then it is grounded. So in that case, it is called on LG. This means single line, on line to ground fault. Now, you see, everybody say this can be this 5 situation. 3LG fault, meaning that all 3 phases shorted plus grounded, The example is the tree fallen on a stormy day. 3 LS, just short circuit among 3 phases because of the human being or animal or whatever reason, and then 2 LG, and then 1 LG. These can be again because of the tree falling, or the 2 LS, the short circuit between two. And why I have written in that sequence, there is a reason. This is the most severe situation, 3 LG1. So, and then this is the least severest one, 1 LG. That's why this is the ranking. So everybody, you can write down in your piece of paper this ranking, that 3 LG is the severest fault, then 3 LS, because you see the difference between these two is that in this case 3-phase shorted in this case, but this is 3-phase shorted plus grounding. That is the most dangerous, because the fault current, because it is shorted, you all said that because this is short circuit, voltage will be 0, but what will be the current? There will be very high value of current, and that current will flow through the grounding system. And if you are here, then you might get shock. That's why 3LG is the most severest, then 3LS, then 2LG, then 2LS, and finally 1LG. This is the severest ranking. Okay, and then now again there are 2 categories. This 2 is on category, and then remaining 3 is the different category. So why this is on category? Because 3LG or 3LS both involve all 3 phases. You see, 3 means that 3 phase, 3 means that 3 phase, 3 line, ground or short circuit. Because they involve all 3 phases, it is called symmetrical fault. So everybody write down that term, symmetrical fault or balanced fault, or it is called the symmetrical fault or balanced fault. So that 3LG and 3LS, and then the remaining is called, these 3 category, they are called the unsymmetrical. Unsymmetrical or unbalanced. Unsymmetrical or unbalanced fault, they are called, because they don't involve all 3 phases. Now in real practice, I mean in majority of the cases, it is seen that these faults occur frequently. Like this is the more common on LG one. Like suddenly a tree has fallen and it touched on and then got stuck with one of the lines, or it might got stuck the 2 of the lines. Then rare cases like all 3 got affected. So therefore, symmetrical fault or balanced fault is kind of the rare. It happens, but rare. But these are more frequent, unsymmetrical or unbalanced fault. And that unsymmetrical and unbalanced fault in the system, it makes the system the unbalanced. And that is the thing in this course at the very beginning, 3-phase circuit, balanced system or unbalanced system, because of these things. We learned those things because to analyze this situation, because in real practice that unbalanced situation happens. So now although unbalanced fault or unsymmetrical fault does not involve all 3 phases, but actually these has much more negative effect on the system as compared to this thing. I mean, these are severest in the sense that fault current magnitude is much higher as compared to this case. In that sense, that is severest. But these faults, unbalanced fault, 2LG, 2LS, 1LG, they have other type of negative impact on the system. So what is the other type of impact? They will create zero sequence current. If you remember chapter 2, 3-phase circuits at the beginning of the semester, they will cause zero sequence current. And that zero sequence current will flow through the neutral of the system. For example, this is a Y-connected generator and it has the neutral. For example, this generator has neutral. This is the neutral line. If any of the fault happens, whatever the location is, some zero sequence current will flow through the neutral line. Or if there are connected devices here and they have the Y connected and they have neutral, zero sequence current will flow through the neutral. But in this case, although the fault current magnitude will be higher, but because they are balanced, there will be no zero sequence current. So the neutral will be safe. Neutral current still will be zero for this one or this one. But these cases are like much more detrimental, or they have much more negative impact. Everybody, could you follow me what I'm saying? Did you all note down this thing? This thing is important. Yeah. That classification of that disturbance of the fault, symmetrical fault and balanced fault, and unsymmetrical or unbalanced fault. You just note down this classification, and this two is this category, and this three is this category. You just note down this one. So now I am going back to that previous pages. Okay, so I was discussing, so therefore due to any fault, so that fault, actually I wrote those things in that slide, this slide. Everybody see that? I said following a fault in a power network, the system might be unstable or oscillating. So like 3-phase to ground fault, 3-phase to short circuit, double line to ground, line to line, and single line to ground. I just discussed these things. And again, this is that according to that severity ranking I mentioned. Okay. Here I have mentioned one thing, everybody see. I said that following a fault, temporary or permanent. So now these faults could be temporary in nature, could be permanent. Permanent means very long duration. Then for example, I was telling you this case 3LG, or this case that a tree has fallen and the branches of the tree got stuck with the 3 lines or 2 lines or with 1 lines. So then in that case, what will happen? In that case, unless the operator or crewman, power engineer, come from the MLGW and fix the issue, the fault is going on, right? Think about the situation. Tree has fallen and its branches got stuck with the lines. So this means that what you will do if it happens nearby your house, you will call MLGW, you will inform MLGW, hey, this is the situation nearby my house. But unless they come, now it might take time, it might take 1 hour, 2 hour, 3 hour, you don't know how long. Immediately they don't come. And they cannot come immediately because again they need manpower, enough manpower. So it might take 1 hour or 2 hour, 3 hours. That long duration is called the permanent fault because it's huge. 1 hour, 2 hour, it's long, very long. By then, like you are under dark, your house is under dark, your all devices got stopped. That is the meaning. But temporary, suddenly you made short circuit, or that animal, squirrel or bat, caused some short circuit. So that is called the like temporary fault. A bird was flying over the lines and it momentarily got short, but then bird flew away. Or as an engineer, you were working, you made short circuit, but you realized. So that is called the temporary fault. So therefore, whatever it is temporary or the permanent, system might be unstable or oscillating. So in this case, system is that generator, that power generator, synchronous generator might be unstable or oscillating. As I said that because of thing, your P value will be changed, your this thing will be changed, and that may cause either acceleration or deceleration. Consequently, synchronous generator might be oscillating and even might be unstable. It may not come back. Ultimately, the system will shut down. So therefore, we are discussing this point that due to any fault on the line, what should be the characteristics of synchronous generator? So I concluded generator terminal voltage drops and oscillates. frequency and speed increase and oscillate, active power decrease and oscillate. And if it is, look everybody, the last bullet, characteristics of induction generator during fault online. So I mean the same thing, only difference, instead of synchronous, here it is induction generator. It might happen that it's a wind generator. Typically, wind generator use the induction machine. Although there are examples of using synchronous machine for wind turbine system, but most of the wind turbine system is the induction generator system. So if it is induction generator, then what is the reaction? Generator terminal voltage collapse down, speed increase, active power decreases to almost zero. So therefore, using, I mean, almost the similar conclusion, but there is little difference. If you see my wording, here I am telling is in case of induction generator terminal voltage collapse down. But here I just said generator terminal voltage drops and oscillates. So the drop, voltage drop means that it went down and then it is oscillating. But this situation is, it is collapse down. Collapse down means it reduces so much that it became almost zero. Fully collapsed down, fully damaged voltage. There is no more voltage. So therefore, this situation is more severe than this situation. And then here I said that frequency and speed increase and oscillate. But here I just said speed increases. I am not using the word like oscillating because this is more dangerous than this one. And then here you see I said active power decrease and oscillate, but here I am using the phrase, active power decreases to almost zero. This means if you compare synchronous generator and induction generator, if it is induction generator, then the situation is more worse. Situation is much more damaging and devastating because voltage collapse down, speed increases very high, active power goes to almost zero. And if this thing happens, if there is no proper control means generator might not come back to the stable position, the previous situation. So therefore, I mean, once again, everybody, what we are discussing the transient and dynamics of electric machines. We are assuming that those synchronous generator, induction generator, electric machines, they are connected to the power network. They are delivering power to the customers and something happened on the connected network. What is the characteristics of voltage, frequency, active power of the generator? That is called the transients and dynamics. That we are looking today. So, everybody, could you follow me so far?
Yeah, I think it's okay.
Yeah, okay. So now I will show you, I will draw the curves and then I will draw the curve for synchronous machine, induction machine. So then once again, I will take you to that board and then again, I will come back here. Okay, now I will clean up because you can see already in the video these things. Let me clean up so that I can draw curves here. So for example, if it is synchronous generator, so everybody see, I will draw that 3 curves. So you also draw with me. First I am drawing the voltage. So here is the terminal voltage, VT, of the synchronous generator, VT. So I am drawing 3-phase RMS quantity. So therefore, for example, everybody see, the voltage was fine. See, voltage was fine. Whatever it is, the level is 11 kV or much higher or much lower, whatever, system was running fine. And at T time, at T1 time, for example, T1 time, suddenly a fault happened. And that fault, any of those faults that we discussed, 3LG, 3LS, 2LG, 2LS, 1LG, whatever the type of the fault, a fault happened, a disturbance happened, all load change happened, and consequently, we are discussing synchronous generator. voltage will drop down first. And then I said it will oscillate. And after a while, it will be settled down. Settle down means it will match with the previous situation. But everybody say, initially the voltage will go down. How much it will go down, it depends on what type of fault had happened. Is it 3LG or 3LS or 1LG? It depends on that, this magnitude. It may not go that much low. It might be this, or even it might go much lower, for example. So but the tendency is that first voltage will go down and then oscillate and then it will come back. But this is very important, that how much it is going down. So depending on the loads are connected here. If the voltage is too much, then the connected device will be affected. So that's why I said that depending on the fault, the magnitude will change. Okay, anyway, so you understood that voltage will go down and oscillate. And then if I plot the power, that P, output power, I'm plotting the power, electrical output power. It was fine initially, whatever the amount is, 100 megawatt or 10 megawatt. And then once the fault happened at this time, T1 time, the power will go low. And then it will oscillate and then come back to the original position after some time. And if I plot that speed, if I plot that speed curve, omega, this one, initially it was fine. It was running, for example, at 3600 RPM, this level, and suddenly fault happened at this point. What will happen? Speed will increase and then it come down and oscillate, and after a while it will settle down. So therefore, this will be the nature, and that I wrote on that slide. So everybody please write down this thing. Now, if it is not synchronous machine, if it is induction machine, so I am plotting the similar curve here, right side. Let me clean up a little bit. I am just removing these things. If it is induction generator, so therefore these plots are for the synchronous generator. In your note, you make like 2 columns of the table. Left side is synchronous, right side is induction. And then exactly similar things I am drawing. What will happen? I am plotting the VT if it is induction machine. So what will happen? I said voltage will collapse down. At this point, the fault happened. So see the difference between these two. In this case, it went down and then again it went up, it oscillating, and then at some point it settled down. In this case, as I said, the voltage will collapse down. It is going down and it is not coming back, meaning that's why I use the term collapse down. Okay, the next, what will be the power situation? The power will also be the similar. It was running fine. Power will be going to close to 0. I mean, very similar things. And then how does the speed look like? How does the speed look like? So as I said, the speed will go up and it will be like that. Therefore, see the difference. In this case, when it was synchronous generator, it went up and then came down, oscillating, and settled down. In this case, it went up. It looks like it is coming down, so might not come down immediately. So therefore, see point by point comparison. I mean, tendency is the same. At first reaction is the same. Once fault happens, it is going down. It is also went down. That matches, but it did not come back. Like if original voltage 11 kV here also, but then it dropped down 2 kV and it remained at 2 kV, like fully collapsed down. The same thing, power went down, came back, oscillating, and then returned back original position. Here it did not come back. And the same thing here, it went up, went down, oscillating, and came back. It did not, it went up. And maybe after a very long time, it might come back, might or might not. So therefore, this is the dynamics of induction generator, and these are the dynamics of synchronous generator. So that is the thing we are discussing today. So and then I will answer you. I think you have one question, that why it is happening in this case, why it is not behaving like that. I mean, you see, everything in the system is the same. All component is the same. The only difference, this machine is synchronous machine, and this machine is instead of synchronous induction. Then it will behave like that. So therefore, I will be answering you later today that why it happens in this case and why they go down and then come back. So therefore, easily you can guess that there is difference in their property, in their characteristics. There is some difference. So we will be discussing today soon. So far, everybody, could you follow me?
Yes, so far.
Yeah, okay. Yeah, you all note down these things. I would recommend everybody, please you note down these characteristics of these and this. I mean, although you can see later in the video, but it is better to note down now this thing and this thing. Okay, and then also let me, you all understand, let me erase these things. Okay, I will tell one thing. I'll write just one more curve. For example, I want to draw that current. When the fault happened, I mean, although I removed the lines, but you assume that the circuit is as it was, and then some fault happened, and then what will be the current? The line current will be very high. We notice that at the short circuit point, voltage was 0 or close to 0, but there will be high value of line current. There will be enough fault current. And what will happen with this fault current that I am plotting? So the fault current, for example, it was running fine initially. Just an example, that 100 ampere was flowing during normal condition. And then this fault happened. So what will happen? Current will go very high. Current will go very high, and then it will try to come down. Next time it will be less, and next time again it will be less. It will go, and finally it will settle down. It will come back at that level. So this will be the current profile. So therefore, typically this first peak, this is called that transient. This first peak is called the transient situation. And when it reduces down around this level, it is called subtransient. And then when it reaches at an acceptable limit, I mean, here it like fully matches with the original position. Of course, this is steady state, but even from here, when it, for example, reaches around 20% or 30% level, there is gap only to 20% or 30% from the, you can say this level is steady state. So steady state situation. Therefore, because today we are looking the transient or the dynamics of machines due to fault on the line. So if I look the current profile, then first what happens? Current magnitude goes very high, and then gradually it come down, and gradually it diminishes. That thing is happening because of this thing, came down, went up, oscillating, and then same thing happened. Current goes very high, and then little magnitude, some magnitude, and finally settle down. So therefore, three things. First peak is called the transient, and then when it reduces kind of 80%, 70%, that is the subtransient, and then when it is at original level or nearby original level, only the gap difference is 20%, 30%, that is called steady state. Therefore, three situations: steady state level, mean that is the safest thing, most safe because it is nearby the original level. And then subtransient, that subtransient is still dangerous for the connected load, connected because current value is too high. This was your rated current, and due to fault, current became maybe 5 times, sometimes 10 times higher, and that is called transient. So therefore, just you will be remembering this terminology: transient, subtransient, and the steady state. Okay, now there are a few more things, and then we'll talk something. We understood this thing. Oh, here I think I wrote that on that I was explaining right now. During a fault, current increases rapidly, transient, and then decreases somewhat, subtransient, and finally reaches at normal or rated value at steady state. So that because we are looking the transient of and the dynamics of electric machines due to fault on the connected network, that's why we are learning this thing. Now, you will be, if you read that chapter 10 or you're listening someone's lecture about this topic, then sometimes the speaker might use some terminology, specific wording like power system stability. And then they might use the word small signal stability or steady state stability and then transient stability. You might see that these three keywords that frequently are being used by the speakers or in the book. So what does that mean? So like for you, I have written, what is the meaning of power system stability? It may be defined as that property of a power system which enables it to remain in a state of equilibrium under normal operating condition and to regain an acceptable state of equilibrium after being subjected to a disturbance. So it's a little bit the long. So meaning is that when you say that a power system is stable, you said that, okay, MLGW system is stable. For example, you said, what does that mean? So this means that is the meaning here, that the system will remain in a state of equilibrium under normal operating condition. This means when there is no fault, no disturbance, nothing happened, system should remain in a state of equilibrium. Equilibrium means under balanced situation. I mean, that equation I was telling you, phi A equal to phi M minus phi. Although that is the ideal, never ever in real practice it will be zero. Always there will be little positive or little negative value, but you assume momentarily that is the meaning of that state of equilibrium. And to regain acceptable state of equilibrium after being subjected to a disturbance. To a disturbance means any of those faults, like 3LG, 1LG, whatever it is. If fault happens and system can return back or can regain the acceptable state. It says acceptable state because everybody say, as I was telling you here that the voltage drops, in this case I said voltage collapse down. So in United States, United States voltage standard is that it should be within plus minus 10%. It should be plus minus 10%. If it goes beyond 10%, upside or downside, then that is the problem. Then similarly, in United States, frequency standard is plus minus 3%. Like frequency here is 60 hertz, plus minus 3% is tolerable. If it goes beyond that level, then that is problematic. So why I am saying that is standard? You see, I said that to regain an acceptable state. What is that acceptable state? If the voltage remains within plus minus 10%, if the frequency remain within plus minus 3%, after being subjected to a disturbance, then we can say that, okay, that system is stable. Therefore, when I say that MLGW system is stable or any power network is stable, meaning that that is maintaining normal operating condition, that is maintaining a state of equilibrium, and even there can be fault or any disturbance, but still that is maintaining an acceptable state of equilibrium or the balance. Then we can say the power system is stable. Or in other words, if the voltage and then frequency, those go beyond, out of those allowed range, then that system is unstable, meaning that there will be lots of oscillation and other thing will go on. There will be impact on the shaft system. So this is that definition of the stability. And then that has two categories: small signal stability and transient stability. So therefore, or sometimes it is called the steady state. So what does that mean? You see, I have written, it is the ability of the power system to maintain synchronism under small disturbances. For example, small variations in load generation, etc. Everybody see the example of this. In your real life, in our real lives, always we are changing some load. You see, small variation. For example, at my home right now, I am using this laptop, I am using some lights. You are doing something, but then again, 30 minutes later, maybe I will not be using this laptop, for example, or I will be cooking, or I will be making a washer dryer, etc. And continuously you are changing something. Those are not big, but they have a small impact in the system. That is called the small signal stability. Now, you are doing something such a way that that is going beyond that range, allowed range. You did something, you made small variations in load at your home, and then that caused frequency beyond plus minus 3%, or voltage went beyond plus minus 10%. Then you can say, no, system is not stable. There is issue or there is problem of the small signal. Small signal means a small change. So if that is too much, if small change is too much, if it is detrimental, adversarial for the system, then that is problematic. Then you can say, no, system is not stable, even though at a steady state. That is the meaning of small signal stability. And then the transient stability means the thing we are discussing today. It is the ability of the power system to maintain synchronism when subjected to a severe transient disturbance. For example, faults on transmission line, sudden increase or decrease of large loads. Like nothing happened, no fault, no disturbance, no thundering, no lightning, nothing happened, but suddenly you change some of the loads in industry. Large load means maybe 50 megawatt load, 20 megawatt load. Suddenly you disconnected or you connected. That will cause the problem. But if the systems come back to synchronism, if the system maintains synchronism, then you will say, oh no, my system is transiently stable. My system can withstand, can tolerate such huge disturbance. Then that is the transient stability. So everybody, could you see the difference between steady state or small signal stability versus the transient stability? Is everybody fine?
So you said that a steady state is more like what's at our house, right?
Yeah. Due to a small change, you see that I said that under small disturbances, you see, it is the ability of the power to maintain sync under small disturbances. Meaning that you see, at our home continuously we are changing loads, right? It is not fixed throughout the day. Sometimes I am cooking, meaning that I am using some load. Sometimes I am not cooking. Sometimes I am watching TV, sometimes not. Sometimes I am taking heat from air conditioner, sometimes not. I am adjusting the setting of that HVAC system, air conditioning system. You see, sometimes you are using For example, at your home, two laptops, three laptops, it depends how many members at your home, 4, 5, whatever, or 2, 3. So everybody is using laptop or not, or one at a time. So continuously there is some change, but we say those are the small variation. So, but as I said, if it is too much, sometimes they have also the negative impact. But if the system maintains synchronism, even though with those small changes, that is called the, okay, system is stable with respect to small signal, or steady state stable. And the transient stability, it is not about those usual change, common change by the customers that is happening always. Huge change, like those 3LG, 3LS faults on the line, or sudden increase or decrease of huge load on the system. If these things happen and your systems come back to the stable condition within an acceptable state, this odd, or it maintains synchronism, then you can say that is the transient stability. That's why transient stability refers to the severe transient disturbance. Small signal stability refers to the small disturbance. I mean, small disturbance, here it is big and short durated. Keep in mind the transient stability refers to severe transient disturbance plus very short rated. It can be for very long durated. You see, because always something happening here. That's the point of interest, the duration can be long. But if it maintains synchronism, that is fine. You can say, no, my system is stable. That's why, I mean, two things are treated differently, small signal stability and transient stability. Although it is short durated, but this is more dangerous, very, very dangerous than this one. So everybody, could you follow me?
Yeah, I think it's pretty clear.
Okay, yeah. And then now moving forward, so like some discussion and some questions. Everybody say, you all write down the answers. I'll be telling you the answer and you will just note down. Yeah. Everybody, during a network fault, draw the synchronous and induction generators terminal voltage, speed, and real power responses. So you see, the answer to this question is just I drew on the board, whiteboard. Everybody, please read the questions and then think about the answer. During a network fault, draw the synchronous and induction generators terminal voltage, speed, and real power responses. So, I mean, if I don't say the draw, if I just say, okay, during a network fault, explain the characteristics of synchronous terminal voltage, speed, real power, then this will be the answer. This and then this is the answer. Everybody see? In words, the answer is this one. Generator terminal voltage drops, oscillates, frequency and speed increase, oscillate, active power decrease and oscillate. And for induction generator, this is the answer. So therefore, in words, that is the answer already here. But here I am saying draw. So this means you have to draw the terminal voltage versus time, speed versus time, and that real power, phi versus time. That I drew on that whiteboard. So everybody, could you follow me what I am saying? So I was telling you to draw those curves, terminal voltage, speed, and the real power. So do you like me to go to that board and show you, or do you remember what I'm saying? Yeah.
I have the graphs written down.
Okay, yeah. So therefore, I mean, for everybody, for just for a moment, yeah. Maybe you got lost. Everybody, just a moment. You see, this is the answer. These three curves, like Vt, phi, and omega. Vt, phi, and omega. So Vt is terminal voltage, phi is that real power, and omega is that speed. Speed slash frequency. Actually, it will be the same thing. speed slash frequency. It will be the same. So you have to draw these curves. That is the answer to that question. I mean, for voltage, so it is going down, going up, oscillating. Power is going down, going up, oscillating. Speed is going up, coming down, and oscillating. And for induction generator, voltage going down, did not come back. Power went down, did not come back. Speed or frequency went up, did not come back. So this is the answer for that one, question number 1. Okay, so now you understood that one. Question number 2, you see, during a transient fault and a permanent fault on the transmission line of a power network, mention the sequence of a line circuit breaker's operation. So this is, again, I need to talk going to the board. Everybody see, first understand the question. During a transient fault and a permanent fault on the transmission line of a power network, mention the sequence of a line circuit breaker's operation. So probably you know that circuit breaker, basically this is similar to fuse at your home. So I think everybody have the fuse at your home. You might have noticed when any short circuit or any fault happened at your home, what happens to the fuse? Fuse got cut. Fuse got cut. And then you need to fix it manually, that fuse, that thin wire. Similarly, along the line, your synchronous generator is connected along the line and then fault happened, whatever it is, transient type or permanent type, the circuit breaker, which is equivalent to fuse at your home, the circuit breaker will operate. What will happen? Circuit breaker, and it is automated. This is not manual, it is automated. Circuit breaker will open, circuit breaker will disconnect the line to disconnect the faulty part. So I am taking you the board. First I am telling just by word. And then after some time, again they will connect back. And if it is permanent fault, again they will open. So therefore what I am explaining here, so let's everybody take you to the whiteboard, then you will understand. Let me clean up these things. Okay, so let me redraw these things.
It does that because it's trying to limit the current going through, right? So if there's a short to ground, it's trying to pull too much current.
Yes.
Okay.
Exactly. So therefore, just I will be drawing that portion, and then everybody see. Right. So therefore, these are the circuit breaker. For example, 3-phase system, and then there are 3 circuit breakers. These are the CB, circuit breaker. And then circuit breaker, basically they look like a switch, this type of switch. Let me complete, and then they are switch, and normal condition, the switch is closed. Think about your fuse. This is like your fuse at home. They are closed. And then the line is going on. Again, after some interval, there are other sets of circuit breakers. Let me draw you, and then everybody will get it, what I am telling. And then, the line is going on. Whatever the components are, like here are that loads, just an example. Okay, and then everybody say this is circuit breaker. These are also the circuit breaker. Again, initially they are closed. Initially all 3 phases circuit breakers are closed. Now everybody say, for example, some fault happened. In this case, 3LS, 3-phase shorted happened. Once fault happened, then what will happen? This circuit breaker will open. You see, Yes, you look. These will open. These will open. Circuit breaker will open. So what is the objective of that opening? That will open so that, now everybody see, that the faulty part, this part got disconnected. So this means that because the fault current will coming from the generator, if you open the breaker, no more current is going, fault current. But here is the thing. Do you think that the circuit breaker will open immediately? It is not. When they are closed, and then you see that short circuit happened here, and then huge amount of oil current is flowing through the breaker. I mean, if you see this on, this is the current through the ICB, circuit breaker. Circuit breaker can tolerate this amount, and once this current went high, and then the breaker will open. But in real practice, those circuit breakers have some sort of relay circuit, which is called protective relay. You might have heard this keyword, relay circuit. And that needs some time. First, I mean, these are pre-programmed. These are automated system, circuit breaker, this relay coil and relay system automated. What will happen? Once there is any fault along the line, there is a controller equipped with the circuit breaker through the relay coil or relay circuit that will understand that something happened, some fault happened, and only then it will open. Only then it will open, not before than that. And that needs some time. So that time is typically, 5 cycles. You can note down that thing, 5 cycles of the waveform. 5 cycle means, you see, this is the waveform, you can see. So this is one time period. This is the time period T. So what is the duration for that? It depends on. So 5 cycle means, so 1 cycle means, so you all know that F is 1 over T. Or in other words, T is 1 over F. So everybody see, calculate 1 over 60 hertz. You will be getting about 16.67 millisecond, the duration of 1 cycle of the waveform. If it is 50 hertz, then you will be getting 20 millisecond, the duration of 1 cycle or 1 time period. So therefore, once fault happened, after fault happening, it takes about 5 cycles to open the breaker. So therefore, that 5 cycle means that 5 multiplied by this one. So you can say about 83 millisecond. That time will be needed to open the breaker. But by then, all connected devices will be affected. So therefore, to protect those devices, the circuit breaker got open. Therefore, everybody say, okay, whatever this number is, after fault happening, within 5 cycles, circuit breaker got opened. And then you say, why the breaker was opened? Because this fault. And then this fault got removed. Now there is no fault. For example, as I said initially, as an engineer, you were working and you realized that you made a short. So, and then you fixed it. Or a bird was flying and then bird got shocked, but then bird flew away. So the fault removed. But for that moment, as long as there was fault, you open the breaker and then now there is no fault. So what will you do? Will you keep them always open in that way? No. You should again reconnect because now there is no fault. Because there is no fault, no disturbance is going on. So if you don't again connect back, then customers will be impacted. So you have to connect. Then again you connect them. Again you connected them. That connection time, when it was opened, and then you are reconnecting, that reconnecting time is, after this time, 30 cycles 260 cycles. 260 cycles. So everybody, could you follow me what I am saying? First, I said that when the fault happened, after fault happening, within 5 cycles, this breaker will open. And then I am assuming that there is no fault got cleared, fault got disappeared. Again, you need to reconnect the breaker. That reconnecting time, after opening the breaker, another 30 cycle to 60 cycle. That is the duration. Some waiting time is needed. So therefore, I mean, everybody, you can summarize in that way. Let me clean up here. You can say, like, you can write down here that like fault occurs. Okay, and then you can say that within 5 cycles, CB opens. Then the next sequence, after 30 to 60 cycles, CB recloses. So this is the sequence. So everybody see that what I am explaining, that first fault happened here. And then I'm talking about the circuit breakers. Within 5 cycles, circuit breaker opens. And after opening, after 30 to 60 cycles, then CB recloses. Why the reclosing is done? Because to maintain the continuity of power, so that the customers are not under that for a long time. This is the thing. And then now everybody see, if it is now, this is the fault and short circuited, I assume that fault has been removed or cleared or disappeared, and then I reclose the breaker. But after reclosing, I mean, these circuit breakers are, very intelligent, very smart. And they are pre-programmed, they are intelligent controller equipped. It is automated. You don't need to do these things manually. Just I am telling you, you don't need to do these things manually. It will automatically happen. And then, for example, it's a permanent fault that 3LS, 3-phase short circuited, or 3LG ground, like a tree has fallen and caused short, and unless the operator from MLGW comes and removes it, it is going on, which is called the permanent fault. Now everybody look, the breaker reclosed after this time, that is fine. But still the tree has fallen and tree is good conductor, still that is causing high current. So again, even though you reclose the breaker, but again high current will flow through this one. So then the circuit breaker, the controller of the circuit breaker will understand, now is still something wrong, something is going on. Again, circuit breaker will reopen. So that's why in that case, then again, CB, reopens within 5 cycles. You see? So this situation is if the fault is not cleared and the fault is permanent. So therefore, first 3 sequences when the fault is temporary. The first 3 plus this sequence, the whole sequence when the fault is permanent. So everybody, could you follow me?
So are you saying these automatically reopen or close?
Yes. Automatically these things will happen.
Okay, because like at your house, of course, if a circuit breaker, if a breaker trips, you have to go manually.
Yeah. But these things, they're not manual. Now, for example, sometimes there are, rare example, because of so much high current, the circuit breaker itself got damaged. Fully got damaged. So therefore, you need to replace the circuit breaker. Because it has relay coil, it has, as I said, intelligent controller. it is connected to that. It's a microprocessor based control. It's huge. I mean, here I am just showing in that symbol like a switch, but it's huge. So therefore, if it is damaged, then that is different thing. I mean, you have to go power engineer, need to go manually and then fix it. Yeah, that is different. But I'm assuming that the circuit breakers are fine. They are operating properly. So it is automated operation. Therefore, these circuit breakers have equipped sophisticated controller, intelligent controller. They will understand that some fault happened. And that fault understanding time is that 5 cycle. It is not immediately it will open. So do you understand? If that 5 cycle means, I was telling you, with respect to 60 hertz, that 16.67 multiplied by 5, which is about, if you calculate, about 83 millisecond. That time is needed to open the breaker. That is the meaning of 5 cycle. And then the next, after 30 to 60 cycle, circuit, like in MLGW, I asked them, they follow like 45 cycles. After opening the breaker, MLGW system needs 45 cycle to reclose the breaker, assuming that the fault was temporary. And then again, as I said, that there are intelligent controller. If fault is permanent, then again circuit breaker will understand after reclosing, no, still something is going on. They will again reopen within 5 cycles. I mean the first condition. And then again after this time it will try to reclose. But again, if it is permanent fault, the case of the tree, again it will try to reopen. That if MLGW attempts 3 times that reopening, after that they understand, no, something really bad thing happened. Then they understand where is the fault, and then they go physically and they remove the tree or whatever the sources of fault, and then they fix it. If everybody, could you follow me? Tyler, is this fine now?
Yeah, it's fine.
Yeah. So therefore, I think we're over the time. Some of you have the next classes. So I want to stop here today. So I will continue this discussion and those questions. So therefore, everybody, this is the answer. What I wrote here, this is the answer to that question. Then I will stop. This is the answer to that question. See the question number 2. During a transient fault and a permanent fault on the transmission line of a power network, mention the sequence of a line circuit breaker operation. Sequence means when it will open and when it will reclose and when it will reopen again. That is the meaning of the sequence. So exactly that thing I told. You have to tell if it is transient fault or short durated fault. Within 5 cycle, circuit breaker open. After 30 to 60 cycle, circuit breaker reclose. And if it is permanent fault, after reclosing, again the circuit breaker will reopen within 5 cycles. I mean, exactly the thing, that will be the answer. Okay, so everybody then hold here until then. I will again discuss. And then today just you got the highlight, you understood something. And in next class, I will be discussing all the answer and then everything will be fine to you. I mean, this chapter, the transient chapter. Okay, so does anybody have any questions, comment?
I actually do. I was quite curious just about our lab finals, just kind of what we would expect for them.
So I think yesterday I sent out an email. You might expect about 5 questions, 5 short questions about the labs.
Just about lab procedures?
Yeah,
Or,
just about the lab procedure, lab theory. Therefore, you all prepared the lab report, right? Yes. And submitted. You all understood the labs. There are 8 labs. From 8 labs, you will be asked like about 5 questions, short questions. I mean, for example, just an example, what is the disadvantage of unbalanced system? Now that falls under the lab number 1, first lab, right? About 3-phase system. what loss can we measure from the transformer test, for example? And this type of short questions will be asked. Therefore, you have 8 labs, so you might expect about 5 questions from 8 labs. That's all. Just you need to write down the answer, but still I have allowed you long time. The questions will be available at 2:30 p.m. and then you must upload on the Dropbox by 4:30.
Okay, perfect. No, I was just curious. Thank you so much.
Yeah. So therefore, all will be kind of pretty basic things about the labs and the theory of the lab. So therefore, you all submitted the report and you have that experimental description available. So you all read those things, and then you already have knowledge about this course from the theory classes. So therefore, based on that, you all will be able to answer. So the questions have been set such a way so that you can answer. Is this fine?